How do continuous and discontinuous conduction modes affect choppers? Imagine controlling the flow of electricity like turning a tap on and off, but with precision to power everything from solar panels to electric vehicles. That's what choppers do in power electronics. They convert fixed direct current voltage into a variable output voltage, making energy management more efficient. Now, the way current flows through the inductor in these circuits can change how well the chopper performs. This is where the concepts of continuous and discontinuous conduction modes come into play. In continuous conduction mode, the inductor current never drops to zero during the switching cycle. This means the inductor keeps supplying current to the load at all times, even when the switch is off. When the inductor current stays steady, the output voltage is directly related to the switch's duty cycle, which is the percentage of time the switch is on. This mode results in a smoother output current with less ripple, making it ideal for sensitive electronics or systems that need stable power. However, because the switch always has current flowing through it, switching losses can be a bit higher, especially at higher frequencies. On the other hand, in discontinuous conduction mode, the inductor current falls to zero before the next switching cycle begins. This happens when the load is light, the inductance is small, or the duty cycle is short. When the current hits zero, the inductor is effectively disconnected from the circuit for a moment. This mode can improve efficiency at light loads because the switch turns on with no current flowing through it, reducing switching losses. But it also causes higher current ripple and more electrical noise, which might requiring extra filtering. The boundary between these two modes depends on the inductor size, switching frequency, load resistance, and duty cycle. Engineers choose component values carefully to operate in the desired mode. For example, in renewable energy systems like solar or wind, the mode impacts how the converter interfaces with the source and load. A solar inverter might operate in continuous mode to ensure steady power flow, while a battery charger might switch to discontinuous mode at low power levels to save energy. Choosing between continuous and discontinuous conduction affects many parts of the design. Continuous mode offers predictable output voltage control and lower ripple, which simplifies regulation. Discontinuous mode can boost efficiency at light loads and allow for smaller, lighter inductors. It also responds faster to sudden changes in load or input voltage, which is useful in dynamic environments. In practical applications, understanding these modes helps in troubleshooting and optimizing performance. If a system shows excessive ripple or unstable voltage, it might be operating in the wrong mode or transitioning unexpectedly. By selecting the right inductor size, switching frequency, and control strategy, engineers can ensure the chopper works efficiently and reliably. In renewable energy systems, this knowledge helps design converters that adapt to changing sunlight or wind conditions, improving overall system efficiency. For motor drives, operating in continuous mode ensures smooth torque and less electrical noise, which is important for sensitive equipment. So, whether a chopper runs in continuous or discontinuous conduction mode makes a big difference in how well it performs, how efficient it is, and how easy it is to control. Recognizing these differences helps engineers build better power systems that are reliable, efficient, and suited to their specific needs.